Consider CMOS process for which L sub min equals 0.18 micrometer, T sub box equals 4 nanometers, mu sub n equals 450 centimeters squared per volt seconds, and V sub t, threshold voltage, is 0.5 volts. Find C sub box and Kn prime. Okay, so C sub box is pretty straightforward actually. It's equal to our permittivity of oxidation, epsilon sub box, divided by T sub box. Now, epsilon sub box, that is just a constant for silicon. It is 34.5 picofarads per meter. Then we'll divide that by T sub box, 4 nanometers. Plug into my calculator. So that is 8.625 times 10 to the negative 3 farads per meter squared. You can also use the unit picofarad per micrometer squared. You'll get the same exact number. Usually picofarad per micrometer squared is more common in actual measurements. Now Kn prime is equal to mu sub n times C sub ox. So mu sub n is 450 centimeters squared per volt second times C sub ox, which is 8.625 times 10 to the negative 3 farad per meter squared. Now, in order to make sure that my units are correct, I'm going to convert everything to meters squared. So we're going to do 450. Notice how it's centimeters squared, so I have to actually do 2 powers. So we're going to do 450 times 10 to the negative 4 meters squared per volt second, multiplied by 8.625 times 10 to the negative 3 farad per meter squared. So we get that Kn prime is equal to 388 microamps per volt squared. Let's solve part B. For an NMOS transistor with a relationship W divided by L is equal to 2.4 micrometers divided by 0.18 micrometers. Calculate the values of V overdrive, voltage from gate to source, and the minimum voltage from drain to source needed to operate the transistor in the saturation region with a current of 0.1 milliamps. So we know that this is the saturation region of operation, so we have a current equation for that. It is I sub d is equal to 1/2 Kn times V overdrive squared, where Kn is just equal to Kn prime times W over L. So that's equal to 388 microamps per volt squared times 2.4 micrometers divided by 0.18 micrometers. So the length units just cancel out, right? So that's equal to 5.17 milliamps per volt squared. So if we're solving for V overdrive, we can say that V overdrive squared is equal to 2 times saturation current divided by Kn, and we can just take the square root of all that. So V overdrive is equal to the square root of 2 multiplied by the current of 0.1 milliamps divided by Kn, which is 5.17 milliamps per volt squared. So I get 0.2 volts. Now, we know V overdrive is equal to 0.2 volts. So how can I find VGS and VDS minimum? Well, VGS is equal to my threshold voltage plus my overdrive voltage. So therefore my voltage from gate to source is equal to 0.5 volts plus 0.2 volts. So my voltage from gate to source is equal to 0.7 volts. And also VDS sub minimum is actually just equal to my overdrive voltage. So VDS min is also equal to 0.2 volts. Okay, let me erase some of this and then we'll solve for part C. Okay, so I went ahead and just made a new slide for part C. So let's get started. Pen ready? Okay. For the device, in part B, find the values of V overdrive and V from gate to source required to cause the device to operate as a 500 ohm resistor for a very small voltage from drain to source. Okay, so I'm going to leverage my transconductance, GDS, which is equal to 1 divided by the resistance from drain to source, which is equal to Kn times V overdrive. So therefore, V overdrive is equal to 1 divided by my resistance times Kn, which is equal to 1 divided by 500 ohms times my Kn, which from part B was 5.17 milliamps per volt squared. Yes. And I'm going to want to convert those milliamps for this problem to make sure my units are correct. So we're going to do 1 divided by 500 ohms times 5.7 times 10 to the power of -3 amps per volt squared. So now all my units are in check. Very important problems like this. So I get the overdrive is 0.39 volts. And again, we can calculate VGS by adding my threshold voltage with my overdrive voltage. So that is 0.5 volts plus 0.39 volts, and that's equal to 0.89 volts. And that solves the problem. Thank you very much for watching this. For any problem suggestions or video suggestions, please refer to my email, and I hope to see you in another video.